Okay, sir, like.
ठीक है.
A very good morning, good afternoon, and good evening to everyone present here. I welcome you all in the second and last session of this third and last day of this international webinar. Now our next speaker will be Professor AKINKUNMI. I request Mrs. Indu to introduce Professor AKINKUNMI.
Good afternoon, everyone. Myself, Indu Bala, pursuing PhD from Punjabi University, Patiala. I welcome our second research person, Bhavantunde Opiluwa Akinkunmi. He is a reader in the Department of Computer Science at the University of Ibadan, Nigeria. He earned a BSc degree in Computer Science and a MSc degree in Physics at the University of Ibadan in 1986 and 1988 respectively. He completed a PhD in Computer Science in 2005 at the University of Ibadan. He has taught computer science for over 30 years at the university level and has been head of the department twice at the University of Ibadan. He was a 1999 Fellow of the United Nations University, now defunct, International Institutes for Software Technology, UNU-IIST, at Macau, SAR, China, and University Development Fellow of UNU-IIST at the School of Computing of National University of Singapore at Kent Ridge between 2002 and 2003. His current research interests includes knowledge, representation and reasoning as well as logic programming system and their various application to normative agent system and constraints of optimization problems. Now I request Professor AKINKUNMI to kindly start with his lecture.
Prof, for your kind introduction. The talk today is about computational constraint solving and optimization, the answer set perspective. I must thank Professor Singh for the invitation, for the kind invitation, and Professor Narendra Singh for the work that has gone into organization as well. Okay. Excuse me, just give me a minute. Now, there are many computationally intractable optimization problems. Now, these are optimization. Okay. That means these are problems that are NP hard, NP complete. An approach for solving these problems is to use approximation algorithms which trade away some correctness for efficiency. There are other such approaches that have been used in solving these problems. The most popular ones, the biologically inspired algorithms, genetic algorithms, gravitational search algorithms, swarm intelligence, like those that Professor Lalas walks around. And there are quite a number of techniques that have been developed along these lines. However, our objective in this talk is to introduce answer set programming as a means of formalizing and solving constraint problems, as well as formalizing and solving optimization problems. Answer set programming, which I will refer to in this talk for much of this talk as AS. LDNF and stable model semantics. And then we will take an example around facility location problem. We will examine the running times and argue that ASP is scalable with respect to running times. So answer set programming has its origin in logic programming, what is known as satisfiability solvers, which can be replaced with stable model computation programs, as well as non-monotonic logic. The logic programming background gives it its language. The satisfiability problems, or the S models, the stable model solvers, give it its ability to compute the key answer sets, and the non-monotonic logic helps it to be able to choose the optimal solution. Now, logic programming is a declarative programming language that is simply embedded in the Prolog programming language. Okay, and satisfiability solvers are computer programs that assign truth values to logical variables in a logical expression. We'll talk more about the stable model computation programs. So in the beginning, there was logic programming. And logic programming is a language that is based on clauses, Hans clauses, from a logical background. A Hans clause is essentially a disjunction of literals. Well, a clause, generally speaking, is a disjunction of literals. That means an ORing of literals. A literal can be positive, like P here, or it can be negative, like not Q here, or not R here, and so on. The not operator in the logic programming system, in the traditional logic programming system, does not mean that Q is not true. It only means that Q cannot be proved. This is different from Q is not true. So a Hans clause is a clause in which there is at most one positive literal. So in logic programming, there are three kinds of statements you can make. A fact can be, you can state a fact, you can state a rule, or you can state a query. Well, a fact can be a very simple statement that something is true. You cannot say, however, that something is not true. Okay? A rule is a Hans clause with exactly one positive literal, and every other literal is negative. Okay? A query, on the other hand, a query is a statement without any positive literal at all. So you are trying to prove P and okay? Facts are the same in both forms. A rule can be in this form, in which there is only one positive literal, in a clausal form in which there is only one positive literal, and it can also be in the rule form, where we are saying here, what we're saying here is P is true if Q, R, and S Hello? Hello? I hope I'm communicating.
Yeah, hello.
Yes.
Yes,
Okay.
Prof, you are audible.
I hear you, sir.
Okay, all right. So that is what the rule means. P is true if Q or R or S. And the query here, which is written like this in the clausal form, means you want to of being able to generalize the various forms of logic programming statements. It's not the same as logical implication. It's a bit of a conditional imperative. So we see examples here. An example of a fact is simply that Bob is male, or that Alexis is female, and that Bob and Alexis, or Bob is a parent of Alexis. And we have a rule here that says father XY, X is the father of Y if X is a parent of Y and X is male. And now we have a query and we want to find out from our query whether Bob is the father of Alexis. Okay, we can infer that Bob is the father of Alexis because Bob is a parent of Alexis and Bob is male, easily from using this rule. But how do we work this out in the way logic programs work? We'll see that shortly. There are two options available to make any kind of inference in logic. There's what is called forward chaining, which starts from facts and work its way towards the goal of what is to be proved. And there's what is called backward chaining, which starts from goals and uses rules to infer facts. And if all the basic facts on the ground are inferred in backward chaining, then the proof is done. In the other case, if by going from facts and making new inferences, if at some point you find the goal, then your job is done. The proof is done. Okay. So logic programs in their traditional form walk through backward chaining. So we start with the query. Okay. What is done is to start with the query and to match the query with the head. So this is the query we started with. Bob is the father of Alexis, is what we are trying to find out. In the program, we have a rule that says if X is the father of Y, if parent X and Y, if X is the parent of Y and X is male. So what we do is to pick up the goal and look at the body of the program to find either a rule or a fact that this can match. So we match this and the head of this rule. Okay. In the process of matching, we come up with what is called a unifier, okay, which connects Bob and X and links X and links Y and Alexis. Okay. Now, having done, if we come up with this unifier, then we have succeeded in matching the head of this with this query. And then we will apply this to the body of the rule in order to get our new set of queries. So our new set of queries is obtained by matching the and that, Bob is male. Okay, so these are the two. Now, with these two new goals, we will pick the first goal, which is parent Bob and Alexis, and then we will continue to see if we can match this. Okay. Interestingly, this matches with a fact, and the fact we have here is parent Bob Alexis. So it means this query is automatically answered, and there is the unifier is empty. Okay, so we do not generate new goals. but we still have one goal outstanding, which is male Bob, and then that Bob is male. Then we pick this up and try to unify, and then we find that there's another fact. Okay, and the proof is concluded. This is a form of the resolution proof for rules. I have avoided talking about the resolution rule for clauses. So this is one of the simplest examples that one can find around. To the facts, and once the facts can be proved, then our work is done. Okay. Now, in order to get an idea of what happens with negation in the course of a program, we tweak this program a little bit, and instead of the rule that says X is the father of Y, if X is a parent and X is male, we change this to X is the father of Y if X is a parent and X is not female. Okay, and then we let everything be so that we can see another example. And in this example, we start as usual. Father Bob Alexis. Bob is the father of Alexis, matches with father XY as usual, and the okay, sorry, apologies. I think somebody wants to annotate. Sorry. So I've approved the request. Okay. So Bob Alexis. So this is what we find out from. This is the unifier that results from this, and then by the time we apply, we now have Bob is the parent of Alexis, and Bob is not female. Okay. Those are the two new goals. The first goal, yes, as usual, we will be able to get this through this and this match, and without any unifiers. And the final goal we have to worry about is not female Bob. Now, how do we execute not female Bob? Not female Bob can be discovered by checking female Bob first, and if female Bob fails, then that is when not female Bob succeeds. So resolution we're not able to prove that Bob is female, then we have to conclude that not female Bob succeeds. So this is true, and our proof is concluded. So, sorry. Oh, I think I have a problem with this now. What do I do? Maybe I should pick an arrow. Okay. Okay, so I can go on now. So the algorithm that is used for logic programming, execution is what is known as SLDNF. The algorithm is selective linear definite resolution with negation as failure. So selective because there's a definite ordering that is respected in choosing what you unify with. Linear because there's only one way by which this resolution is done, and you do not have multiple resolutions being carried out all over the place. Definite because it can take care of definite logic programs without negation, and with negation as failure because when it comes across negation, it can treat negation, it can handle negation, it can investigate negation when what the negation is about fails. So the negation is true when the negation itself fails. Okay, so that's it about SLDNF. Okay. SLDNF, however, has a drawback. It can succeed when you have a stratified program, but it will not succeed when the program is not stratified. Now, a program is stratified when you can divide the program into stratums, into different stratums, okay? Of any rule has been resolved at the previous stratum. So, for example, here we have not Q, okay, but not Q does not exist anywhere higher than this, okay? So we're not going to have a negation of anything here that is at a higher strata, okay? But we can have the negation of something in the body of a rule here that exists at a lower stratum, okay? The same thing here, not S. S would have been resolved at a lower stratum here. So we can stratify a program. The problem that SLDNF will have is when you are trying to deal with a program in which there is no stratification. An example of that is here. For example, Fido is a person, okay? And a man is a person that is not a woman, and a woman is a person that is not a man. Now, this is a problem because we have a mutually or a circularly definition of negativities or negation that mutually involves two rules. So man here depends on woman, failing. And in the definition of man, it depends on the definition of woman failing. And the definition of woman also depends on the definition of man failing. In this case, SLDNF fails. Excuse me, please. And so in going forward, stable model semantics were invented in 1998 by Vladimir Lifshitz and Michael Gelfand. And they got around this problem by calculating the stable models for programs that are unstratified, such as this. And how do we calculate the stable model? The stable model itself is defined as a fixed point. Okay, it's defined as a fixed point of what is known as the Gelfand-Lifshitz operator. So we look for a set of literals from this program that we can show to be a fixed point of that operator. So it's a fixed point kind of semantics. An example of this is person Fido, man Fido. The second example, of course, is person Fido, woman Fido. And the way to prove this is to look at the program and first remove all the negation of literals that is not in this set. Okay? All the negation of literals that is but we will delete the negation of woman Fido. That is this particular literal, not woman Fido. So that is what we did there. Sorry, apparently the annotation has messed things up a little bit. So here we are. The not woman Fido is deleted. Okay. Maybe I can remove this, but I don't think I want to waste too much time. Okay. The second stage is to remove all the rules that has in its body the negation of any literal that is not present in the set. So we will now remove this rule because it has in its body the negation of not man fido, which is in this set. Okay, and after removing this rule, what does that, what happens? It means we have only two rules left, only one fact and one rule. As a matter of fact, person fido, man fido, person, so person fido if man fido. Okay, and if we compute what comes from this, then we have person fido is to ground. Okay, we will have to ground the program, and so the grounding of the program is this. Yes, this is the grounded program. The grounding of the program means we replace all the variables with the and make an appropriate rule. So starting from this rule, man X, person X, man X if person X and not woman X, we come up with this rule, man fido, X replacing fido, apologies, fido replacing X, man fido if person fido and not woman fido. Similarly, the woman rule is replaced appropriately, woman fido if person fido and not man fido. Now, with the grounded logic program, we can then apply the GL operator in stages, stage 1 and stage 2, and then we can use that to prove that any given set is a fixed point, or to investigate whether any given set is a fixed point or not. So there are already programs that are able to compute stable model semantics. The most popular of this is the program by the group in Helsinki at a particular point. I don't know. I think I have that somewhere here. Already there are methods for this that has been carried out. Okay, I think I'll show this later. So answer set programs now extends logic programs by introducing various kinds of statements. The first thing that answer set programming language introduces is the negation operator, the classical negation, which means P is false. This is absent in the logic programming system, the logic programming language. This is absent, but is now in answer set programming. So this is there. Now, apart from that, there is the hard constraints rule, which says that false if P and Q. The implication of this is that if P and Q are true, that P and Q must not be true. So we look out for any statement in which P and Q is true, and we eliminate that answer set. So if you have any answer set in which P and Q is true, not valid. So it's not, so P and Q should not be true. Okay, P and Q should not be true. Right. Then there is the choice rule. Okay, in the choice rule, it means if P is true, then pick RST. Pick one of R or S or T. Now, there are different variants of this. You can choose, you can decide how many of these you want to be true. So this rule, for example, is saying if P is true, choose a minimum of 1 and a maximum of 2 of R, S, or T to be true. And this version of the rule is saying that if P is true, then choose exactly 2 out of RST to be true. Okay, we will see variants of these rules as we go on. Now, a very important statement, extension, that helps us to carry out such that Y has this property. Okay. Now this chooses answer sets with the least value of Y that satisfies the property P. That's what this statement is saying. Now this statement is very useful for optimization. The choice statements are useful for enforcing constraints, integrity constraints, if you like, and they are called hard constraints. When you are programming ASP, these are called hard constraints. And these ones that have to do with optimization are called soft constraints. Now, these are some of the extensions that you have in ASP added to what exists in logic programming that is useful. There are other interesting extensions that we will come across. For example, this is talking about choosing the maximum value that satisfy a particular property P. That is what this is about, or a minimum value Y that satisfies the property Q. Okay. It can also say count the number of X's that satisfy the property QX, the property Q, sorry, or you can sum Y, all the Y's that satisfy property P. We will see examples of this as we go on, particularly in our example. Okay. Now, I'm using this just to illustrate the choice rules with variables. This is a choice rule. This is like a fact because it doesn't have a body, but it's a choice statement. It's a choice fact that says elect 3 persons. Okay, it's saying elect 3 persons. So we assign elected to 3 individuals that satisfy the property person randomly, any 3. Okay, any 3. So there will be different answer sets generated here, in which for each answer set, there are exactly 3 people that are elected, and each answer set will be different from the others. Okay, and then this is saying we should elect 3 persons into every committee. Now, this is a rule. It says if C is a committee, okay, for every committee, if C is a committee, elect persons into the committee. So we say we have elected XC and elect exactly 3 persons into each committee. Okay. So those who are computer science, who have a computer science background will probably know, or who have a programming background of any sort will know what is called a local variable. So in this example here, this is an example of a local variable because it's all within the scope of the head of a rule. This is global in the sense that it extends beyond the head, and it goes into the scope extends to the body as well. Okay, so now, how does ASP work? Simply, just as we've seen, ASP, the first step is to ground your answer set program, and the next step is to compute the stable models. Okay, and the final step basically is to take the stable models and report them as answer sets. Okay, This is how answer set programs really work. Okay. However, if you need to optimize, then there is a fourth step in which you select among the stable models which answer set is preferred above others. So the most preferred answer set will then be reported. So this gives way to what is called a guess, check, select methodology. The guess optimization in mind in a paper called the Answer Set Primer. So what they did is to generate candidate answer sets, okay? And this is a general methodology for doing answer set programming, which is quite popular. Generate candidate answer sets, check the candidate answer sets for conformance with hard constraints of this kind, and then select the optimal answer set from among these using soft constraints like this one here, to minimize, to select among the answer sets that has the minimal value of x for which P of x is true. Okay. So having done all this talk about answer set programming, we will now come to our example. Our example is a facility location problem. Now we want to make an optimal choice of sites for some facilities, for a number of facilities among candidate cities. Okay, so there are a number of cities and there are a number of facilities that we want to distribute into these cities in an optimal way. Now, in the first place, there's a fairness criteria that no city should host more than one facility. We don't want one city to host more than one facility. Okay? That's a fairness criteria because we don't want these facilities concentrated in one place. The next criteria is that there's an optimization criteria, which means as much as possible, facilities should be located such that the overall cost of accessing the facility from all the different cities is optimal. Now, in talking about the overall cost of access, we're thinking about cost of transportation, basically, or the costs of transportation, not just in terms of distance, but in terms of a measure that describes the difficulty or the easiness of access. Okay, so we can now describe our problem scenario. There are cities. Okay, there are cities. Each city has a capacity which we cannot exceed. So these are example facts. There are cities, there are facilities. Each city has a capacity. Okay. Now, each facility has a requirement that eats into the city's capacity. So we have capacities. Now, so if we cite this facility here, any facility we're citing must have enough capacity to absorb the facility. And then, of course, we have excuse me, sorry. So we have the demand that a facility places on a city. Each facility places a demand on the city. Our first step is to generate candidate solutions. And to generate the candidate solutions, we need the choice statements that we have seen earlier. And now the idea here is to assign exactly one facility to a city, okay, for every facility must be assigned to exactly one city, okay? You cannot assign a facility to different cities. You cannot assign the same facilities to different cities, so we're assigning every facility to an exact city. Now, this will generate an assignment in which every facility is assigned to one city. Even though it may be assigned to different cities in different answer sets. So that is it for guessing. Okay. So the next step is to check candidate solutions. Now there are three hard constraints involved here. Let me try and see if I can remove some of these lines because there may be a problem. Sorry. My apologies. I'm trying to see if I can get rid of these lines and they don't become a problem. Okay, so I think we can continue now. So the first check is to see that no city can host more than 2 facilities. And there's a hard constraint here that checks that if a city is allocated to different variable, if there's an assignment to the same city of different variables, different facility variables, F1, F2, then it must mean that either F is equal to F1 or F1 equals to F2, so that that city in the end does not have more than 2 facilities allocated to it. So we're saying if F is assigned to C, F1 is assigned to C, F2 is assigned to C, and F is not equal to F1 and F1 is not equal to F2 and F2 is not equal to F, then this is something we want to avoid. Okay, this is something that we want to avoid. We want to avoid the situation in which 3 facilities are allocated to one city. Okay, so this will take care of that situation so that no city can host more than 2 facilities. The second hard constraint, in the second hard constraint, we are trying to check to see that the total capacity, the total demand that the number of facilities allocated to a city makes on that city is not anywhere more than the city's capacity. So if this is the city's capacity, N, and we calculate from these 2 prologue rules the total demand on that city from all the facilities allocated to it, okay, and this is the total demand, that the demand is not I'm afraid I have to decline because but I can send you the slides in the process. It would have been nicer to be able to share the slides before the talk than, okay, let me approve and I'll be more careful, okay, that I don't, okay. All right. Okay, so this is the second check to see that if you allocate a number of facilities to a city, that the city can accommodate it. sorry, this is my own. Okay. So that is the second check. Okay. That's the second major check, the two-hat constraint. No city will be allocated more facilities than it can handle. Okay, no city can be allocated the facilities that it can handle. So the final step is to select. And the process of selecting means that we need to calculate the distance, the weighted distance, the weighted cost of putting a facility in a city. Okay, that is calculated from here. The weighted cost of putting a facility in a city is the sum of the weighted distances from every city to the city in which the facility is hosted. Okay, so the weighted distance between the city and the place where the facility is hosted. Now, in the process of doing that, this is what we do. We assign our facility. We check the assignment of the facility, the host, okay? And we must calculate the weighted distance from every city to the host city of that facility. That is obtained from the weights. That is the amount of demand from each city is multiplied by the distance. So the demand for service is the weight that we use to multiply the distance in order to get the weighted distance. Okay, and then we calculate the weighted cost of choice, okay, for each facility, and that is done in terms of the weighted distance, which is calculated earlier. So in the end, what we're trying to do is to now take together the total cost of all the choices by summing together the weighted cost of choice for every facility. So the sum of the weighted cost of choice for each facility is summed together, okay, and okay, it becomes the total cost of choices. Now, in order to optimize, what we want to do is to minimize, is to choose the model with the least value of t that satisfies total cost of choices. So, in other words, what we are saying is we are choosing the model among the answer sets that will give us the least, okay, the least amount of the total cost of every choice. So that's the total cost of every choice will be calculated, and then we will choose the model with the least cost. So computation power. It was implemented on an Intel Pentium N350, 2.16 gigahertz with 4 gig memory RAM, 64-bit operating system. It's running Windows 10 Pro, which is a bit heavy for it. And then we implemented this in Bingo, and we got the running times. And these are the running times we have. If we have 5 cities and 5 facilities, the time to solve is 0.02 and the CPU time is 0.109, and so on and so forth. Well, we could have used a more sophisticated system, but for the purpose of experimenting for the viability or the scalability of these of the answer set solutions, even in the most basic computational environment. So this is what we have. This is the running time we have for five cities and 5 facilities, 10 cities and 5 facilities, 15 cities and 5 facilities. As we increase the number of cities, though the overhead seem to increase, but the pattern in the solving time is not substantially different. Yes, it's not substantially different. So this is one set of results. In another set of results, we raised the number of facilities to 10, and we varied the number of cities. Again, the pattern remains similar. Solving times and the CPU times. CPU times shows some overhead, but the pattern is not, again, substantially different. In experimenting with this kind of things, solving times, running times, we need to run this substantially many times and get the averages. But we're still working on some of these so that we can get a more reflective average. But these are some of our initial results. So what do these results show? These results show that realistically sized problems, okay, can be solved in decent time using answer set models. Okay. So if we move to a system with some higher capability, we're likely if we move to a system with a higher capability, we're likely to get better results. And all these were achieved in an environment with very modest computational capabilities. So we can move to a higher system and get even much better. So to summarize, I hope I've not taken too much time. To summarize, ASP provides a very useful technology for modeling and solving optimization problems. Using ASP allows us to encode and enforce other forms of domain requirements, such as fairness criterion, in addition to computing optimization. This is a major advantage that using ASP has over other approaches, because we are able to include the knowledge factor, encode aspects of knowledge, as well as enforce other forms of common sense requirements, if you like. The running time suggests that ASP as a mechanism for solving optimization problems is scalable with respect to running times. Okay, so acknowledgement. I want again to thank the organizers of the webinar for their kind invitation. I want to thank my MSc students of the last 2 sessions for working with me on various applications of answer set programming. And I want to thank Mr. Emmanuel Ngbeahu-Ruike, who is my MSc student, for working with me on the facility location problem experiments. Thank you very much for listening.
Sir, thank you for your thought-provoking and motivational lecture. Now participants can ask their queries from Professor AKINKUNMI. You can ask your queries in the chat box also. Participants can send their queries to organizer or resource persons on email or WhatsApp.
I didn't get the question. Sorry? Hello?
Is there any question or query from the audience? I thank Professor AKINKUNMI for his words of wisdom. There is one query in the chat box, sir.
Okay. Let me stop sharing. I don't know if this will help. In chat box.
Yes, sir. The query is, how can we
There's a
apply
question on the
ASP?
chat box.
Okay, yes, I see the first question. How can we apply ASP in bioinformatics? Yes, ASP has been applied in bioinformatics in several ways. It's been used, ASP and logic programming have been used around answering questions about phylogenetic trees. I'm aware of that. And I think there are other applications for which ASP has been popularly ASP in bioinformatics that already exist. Whether it will be new or not, I don't know, but because quite a number of people have worked around ASP in bioinformatics. The second question is, what is the mechanism around the, sorry, I didn't get that question. Sorry, I have to go back. What is the mechanism behind using the application you presented? Okay, yes, the mechanism is a little bit of an extension of logic programming. But the primary mechanism really is about fast SAT solvers were, well, the age of the modern SAT solver began in 1992 with a paper by Bart Selman and Henry Kotz. There's a paper around that. I can send you that if you want. You can send me an email. But since then, SAT solving has become a major competitive task around the world, and every year new SAT solvers are invented which are faster than the older ones, and this has made answer set programming continually faster. So by the way, anyone who is interested in logic programming should you get closer to the Klingo group at University of Potsdam, that's where, well, I also use some of their facilities. They are available online. You can Google mechanism really is around SAT solvers. As I said, programming has benefited from the improvement of SAT solvers over the years. Okay, I think that's the only, those are the only two questions I can see.
So the next question is in the chat box. What is the rationale behind the application in real life problems?
Okay, the rationale, sorry. Okay, what is the rationale behind the applications to real life problems? Yes, the advantages of ASP, there are advantages for ASP over some other mechanism. Yes, there may be some difficulty with picking up a new logical programming language, which may be a disincentive. But one good reason to do ASP, to use ASP for optimization problems, is the fact that it can offer the knowledge advantage. Okay, you can codify common sense knowledge as a means of choosing your optimal values, mitigating your optimization choices. For example, in the example we showed, we don't want one city to host more than one facility. Okay, we can come up with different common sense criterion that we can use to mitigate our optimization choices. On the basis of that, we're not just doing optimization, we're also able to tamper optimization with a number of social choices that may go down well with the stakeholders. This may not be possible when you are using some other algorithmic or mathematical technique for optimization. So this is one good reason why you may want to use answer set programming.
Thank you, sir. There is one more question. In what condition or field ASP can be applied?
Oh, well, ASP can be applied once the problem is well defined, once we know, once we have an idea of the domain, once the domain is well understood, whether we're able to mathematically express the domain or formalize the domain mathematically or not, yes, we can use ASP. Once we have an idea of, once the domain is well known, whether we're able to formalize it mathematically or not, we can apply ASP.
So the next query is it possible to apply ASP for resource allocation under risk?
Yes, yes. This is one of the problems. Well, we have applied ASP for some task allocation problems recently. We have applied ASP for some form of resource allocation recently. We're working on something that has to do with fair load shedding. That's also one of the things that my group has worked on. In fact, any problem that is a hard optimization problem, is a problem for which ASP can be applied.
Next query is, can ASP be used for tuning PID?
Sorry, I didn't get the question. Dr. Jane?
Yes, sir.
Sorry, I didn't get the last question.
Yes, sir. I am repeating. Can ASP be used for tuning PID?
PID. Sorry, I don't think I'm aware of that domain. PIDs. Sorry, I don't think I know the domain personally, but I can try and investigate.
Okay, sir. The next query is, we apply ASP in research, such as running statistical analysis or collection and manipulation of data? Yes, sir. The next query is, can we apply ASP in research, such as running statistical analysis or collection and manipulation of data?
Sorry, I didn't get the last part of the question, but running statistical analysis, probably not. That's outside of the scope of optimization, I suppose.
Okay. All next queries can also be WhatsApp on the contact number or on the mail of Professor AKINKUNMI. Thank you,
Okay.
sir. Thank you,
Yes, ma'am.
Professor AKINKUNMI, for your wonderful and informative talk. Now I request to the host of this webinar to award the certificate of appreciation to Professor AKINKUNMI. Thank you, sir.
Thank you very much, sir. Thank you,
Thank you,
ma'am.
sir. Now I request Professor Satyabir Singh, convener of this webinar, to say some words of thanks to Professor AKINKUNMI.
Hello, everybody. Before thanking Professor AKINKUNMI, I should first thank Internet. Am I right? Anyways, thank you so much, Professor AKINKUNMI, for taking time out of your busy schedule to visit our university virtually to share your experience with the students. Everyone present at the event learned a great deal through your talk. Your talk not only gave valuable insight into optimization with emphasis on logical programs, resolution proofs, ASP, and related results, but also inspired many to actually do their effort for the same. We are very thankful to you, sir.
Thank you very much, sir.
Now I can see that in the audience, my dear friend Professor Kirtivant Gadle is there. He is professor and head Department of Mathematics, Baba Saheb Ambedkar University, Maharashtra, Aurangabad. I had invited him as a resource person, but due to his busy schedule in the university, he could not spare time to deliver his invited talk. I am happy to share with everybody that he falls in top 2% scientists of the world. Now I request Professor Gadle to share his views about the webinar. Professor Gadle, please.
Thank you very much, sir. Thank you very much to give me an opportunity to share my views regarding this international webinar. So, first of all, I am congratulate to organizer, Professor Satyabir Singh, Punjabi University, Patiala, and his entire team, whole entire team, organize such a beautiful international webinar in India. Sir has give on one platforms to organize the uh, 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 organize the intelligent optimization technique. Now I see that this optimization technique is used everywhere and every field, and this has real life applications. And mostly on this in this webinar, sir has invited that some resource persons from Romania, from Kusumdeep, IIT Roorkee, Isan S. Hossain from Egypt, and that is Babatunde Akinkunmi from Nigeria, and from South Africa, and from various countries, and deliver the lectures on optimization technique and their real life. That optimization technique. And actually you have to that is my research students have doing some real life problems, like I will tell you that one of the in Maharashtra, if you have to heard the Ashtavinayaka Yatra. So one of my students is working on that optimization, that is on this problem Ashtavinayaka Yatra. That means you have to start journey from which. So Ashtavinayaka Yatra means Theur, Ranjangaon, Mahad, Pali, and so on. So at which place you have to visit first, and after last one, with minimum time and with minimum cost, and also apply the MATLAB technique, MATLAB programming. So you have to get the wonderful results. Okay, so this is actually the real life problem he has one taken, and one of the problem is also take the laptop selection problem. So in laptop selection problem, you have to see that there are various laptops available in the market, like HP, Dell, Apple, and so on. And you have to take the configuration like that screen, which is 14-inch, 18-inch, 21-inch, and so on. Then memory, hard disk, then RAM, then this particularly, if you have to that is purchase the laptop. So which configuration actually you want? So you have to take again that divided some. You have to use for engineers, you have to use for professor, or you have to use for general. So while if you have to go to market and if you have to select the laptop, so you have to apply our own techniques, our own algorithm, and you have to find out the solutions of that laptop also. So which particularly you choose or you purchase the laptop for your use. So such type of problem you have to that is take. That is, these are actually the real life problems. So you have to take and solve, and you have to doing the MATLAB coding also, and you have to get the such wonderful results. So I thought many of the areas that is optimization technique are used. Okay, so in every subject also, in every subject and every field. Okay, so this techniques, optimization technique that is used. So some of the my request is to some of the newly researchers to find out such type of problems, real life problems, and you have to do that is find out the solutions in new way. Okay, so I'm very much thankful to give me an opportunity to share my views. Thank you very much, sir.
Thank you, sir. Now I request the host to greet Professor Girdley with a bouquet. Thank you, sir.
Thank you.
I request the host to award the certificate of appreciation to Professor Girdley.
Thank you, sir.
Thanks all. We all will be meeting after 15 minutes for valedictory function. Thank you all.
Dear participant, we will resume the meeting after 15 minutes. Please don't leave the meeting. We are